All right. Hello, everyone. Welcome back to the Church of Logic. I'm your host, Cody Rue, and today we're going to finally get into the nitty-gritty of it all and talk about first-order logic. So, all right, so far we've stayed pretty abstract. We've said logic is just some way of writing down syntax, just sort of strings of characters which have a meaning about something which you expect is true in mathematics or even in the world, right? Saying that, uh, there's an infinite number of primes, right? This is sort of a sentence you can write down, and in a formal logic, it's something. It's something that you want to be able to express, or at least you want to be able to express things that talk about the truth of the world, and then you want to be able to prove some things and not be able to prove some other things, right? If you can prove everything, then your system of logic is a little bit boring, and of course, if you can prove nothing, it's even more boring. But you just want to be able to prove some things, right? You want to prove that there's an infinite number of primes, but you don't want to be able to prove, that all numbers are prime or something like that. So, like I talked about previously, people would come up with this very abstract definition of logic. But, let's get more concrete and talk about first order logic as, it's generally construed by logicians and mathematicians. First order logic isn't the only logic you can consider, right? It's one of many, many types of logic that all sort of fall under this big umbrella of things you can talk about with derivation rules, and where the derivation rules are this kind of algorithmic thing where you can check whether a proof is correct or not. But first order logic has kind of the distinction of being the one people have studied the most, and the one that's sort of this de facto base logic for almost all people that work in mathematical logic, and people that work in mathematics really they base their intuition about logic on first order logic. And I'm going to explain what that is, and this will allow us to explore different kinds of logic, but also to explore the basic things people really care about when they're studying logical systems, because we'll have a concrete example, and then we can sort of see where the different systems deviate from this concrete example. So I think I'm going to adopt sort of the programmer's view. I think programming, has become almost something that everybody has this sort of passing familiarity with. And I'm assuming, a lot of my listeners are familiar with programming. So maybe it's useful for me to define first order logic as this kind of programming language. Because, really, when I talk about, a syntax that allows you to state things about the world, and then a precise, set of rules for derivation, this is kind of what a programming language is, right? You have a syntax for programs, and then you have a set of rules for executing that program. So, at the very least, we're in the same realm of types of things we're talking about. So if first order logic were a programming language, it would definitely be a programming language where the most important type of things is Booleans, is truth values, right? Logic is there to just talk about truth values. In a programming language, you want to do computation, you want to print things on a screen, you want to return numbers, you want to return, functions or file handles, or communicate over the internet. Let's say you restrict your language, you say, okay, the only thing you want in your program is returning a Boolean, right? Returning true or false. That's what first order logic is, right? A programming language where the main thing you want to do is just return true or return false. And what do you have to write programs with? Well, you can declare constants, right? You can't really define them, but you can declare constants. You can declare relations and functions. Functions are things that take in, constants and return other constants. Or more notionally, they're things that take in elements of your universe, right? You have this sort of implicit universe of all the things you talk about, right? That those, you can think of those as like numbers, or objects, or people, or just abstract things you can talk about. And functions take those, return other ones. And then relation take a bunch of those objects and return a Boolean, right? So you can declare these. You can say f is a function, r is a relation, and you can say it's a relation that takes in two things and returns a Boolean. And you can say it's a function that takes in five things and returns one thing. And you can even see constants as functions that take in zero things and return an object. So okay, so we have these objects. We can declare these functions. We can declare these constants. We can declare these relations. And then you can just sort of say, okay, and now we have all the usual Boolean combinations, right? So we have the and the or and the negation, and you can just use those to build up different combinations of Booleans. And finally, you have this really powerful construct called universal quantification, right? Which just takes in a parametrized relation, right? So a thing that takes in an object and returns a Boolean, right? You can think of that as it's just a Boolean, but where there's one thing that's uninstantiated, one variable in there that sort of doesn't have a given value. And then you say, okay, well, for every possible instance of that value, the thing is true, right? And in programming, this is very familiar. You often want to iterate through a list or iterate through a collection of things and then check some Boolean for every individual of that collection. But you have to imagine that the set of all objects is infinite, right? So the implementation morally is going to be less obvious, right? You have this infinite set of things that you're iterating over. And then dually to that, you have the existential quantifier, which takes in a parameterized relation and just says, this is true if there is at least one thing that satisfies this relation, right? So, in some sense, first-order logic is very simple. At least its syntax. It's just these, declare these parameters, these constant, these functions, these relations, have all the sort of ordinary Boolean combinations of those, and then have these quantifiers that say every object satisfies this property, or there exists an object that satisfies this property. Okay, I haven't really talked about free versus bound variable, but I don't think this is really that important. You can just really sort of consider that we're talking about things that are undetermined, and then for all, takes a thing where one variable is undetermined and makes it just a Boolean, and so does exists. All right, but this is just the syntax, so let's talk about the rules for a minute, and I'll leave further consideration of this later. So one thing that's obvious is for the Boolean part of the logic, just for the Boolean combinations, the rules shouldn't be too hard. You just want rules that say, if two things A and B are true, then the combination A and B is true, right? And if one of them is true, then A or B is true. And then negation is a little more complicated, but it's basically saying that if if A is true, then you get a contradiction, then actually not A is true. And then you sort of add these rules, and they're quite reasonable, just to talk about the Boolean combinations of things. And then what's more subtle is the universal quantifier. The existential quantifier is not quite as subtle. If you want to prove that there exists something such that a property holds, you just have to find one, right? You just say, okay, I have a property, about an object, and it holds, in the case of that object, equals, f of x or f of some constant, right? And then you say, okay, well, then I've proven there exists some y such that property holds, right? It's very simple. You just sort of say, I have an example, therefore there exists one. But for universal, you can't do that, right? You can't say, oh, this holds for all possible examples, because you know, you can't list them all. It's this potentially infinite set. So what you do there is you say, I know that this holds of a generic object. I know nothing about this object, and yet I know that this holds. And then you can conclude that it holds for all possible objects. And I think this is kind of a very deep observation, which was made, you know, really at the beginning of logic, that if you can talk about a generic object and say this holds for a generic object, then actually what you've done is proven a universal. So, yeah, so this is sort of a rough description of all the provability rules for first order logic. I'm going to talk more about that in the next episode, and I'm going to talk about the relationship between these rules, which sort of seem sort of artificial way of like building different provable things, and the actual semantics, which are what we actually mean when we talk about, you know, a proposition in first order logic and what it means for that proposition to be true. All right, see you next time.